Hello, my name is Scarlett Raine, and in this video I introduce our paper, Image Labels Are All You Need for Coarse Seagrass Segmentation, accepted for presentation at the IEEE CVF Winter Conference on Applications of Computer Vision. This is work completed in collaboration between the QUT Centre for Robotics and CSIRO's Data 61. Seagrass meadows sequester large quantities of carbon and are critical ecosystems. Detailed data on seagrass meadow species composition and extents is needed for accurate estimation of carbon sequestration. Robotic vehicles can be used to survey seagrass meadows. If equipped with machine learning methods, survey paths can be dynamically adapted in real time. Seagrass meadows are complex and cluttered, with many overlapping instances. Boundaries are poorly defined, making it extremely time-consuming, costly, and difficult for domain experts to manually label every pixel or draw polygons around every instance for training a model to perform semantic segmentation. Instead, we propose using image-level labels only to reduce this annotation effort, while at inference time, we want to still perform coarse seagrass segmentation. This coarse grid-based form of segmentation still provides spatial information about the position and abundance of species in each image and is sufficient for estimating species composition and extents for seagrass meadows at large scale. We believe coarse seagrass segmentation from image-level labels achieves a good balance between minimizing annotation cost and effort for training, while still obtaining useful, sufficiently detailed analysis at inference time. In this work, we use seagrass images containing just one species at a time, so that we can leverage the image-level species labels during training. Prior approaches for multi-species detection and classification of seagrass in underwater imagery have been trained on patch-level labels, where every small patch for training requires its own class label. Some prior approaches assume these patch-level labels directly from the image-level label, which introduces noise into the dataset. In this paper, we remove the need for those patch-level labels altogether and instead present our principled approach, which uses only the image-level label at training time, while still performing coarse seagrass segmentation at inference time. This prevents the incorporation of noise during training and reduces the annotations required by 96% for the DeepSeagrass dataset. We introduced two methods for weakly supervised coarse seagrass segmentation. We will later see that the two methods are complementary, with the first method having higher overall accuracy, while the second method behaves more conservatively when classifying visually unclear or degraded patches. The first method is called SeaFeats and is based on contrastive training and feature similarity. We first train a ResNet 18 feature extractor using the SimCLR unsupervised contrastive pre-training method. Every epoch, we calculate a set of per-class template feature vectors. To do this, we use that ResNet 18 feature extractor to obtain feature vectors for every patch, and we average the L2 normalized features of patches belonging to each class at the image level. Then we can use the cosine similarity between each query patch feature Vx and the corresponding template feature vector Vc, and we use this similarity to determine the class of patches within each image. Then we use the patch pseudo-labels Px when fine-tuning the whole architecture end-to-end. We also dynamically update the class template feature vectors every epoch as the model is trained. The second method is called SeaCLIP, which demonstrates that the CLIP large language model can be used as a supervisory signal in domain-specific applications. Here we take CLIP and we use it as a pseudo-label generator by querying CLIP with natural language prompts describing either seagrass or background. We then use the CLIP pseudo-labels in conjunction with the domain-specific label to train a ResNet 18 feature extractor and classifier. Finally, we combine the two methods together in an ensemble to form our final architecture. To explain why we use an ensemble, we can inspect the test results on the DeepSeagrass dataset. We see here that combining the two methods in an ensemble improves F1 scores from 93.1% for SeaFeats and 87.8% for SeaCLIP to 95.3% for the ensemble. We can understand the reason for this by inspecting some of the model inferences. Here we observe that SeaCLIP is more likely to classify visually degraded, discolored or blurry patches as background, rather than confidently misclassifying the species of seagrass. Although SeaFeats has a higher overall accuracy, combining SeaCLIP with SeaFeats reduces incorrect species identification for these visually unclear patches, resulting in overall improved robustness of our method. For the multi-species case on the DeepSeagrass dataset, we improved from 88.5% for the previous state-of-the-art to 95.3% for the class-weighted F1 score. This is an improvement of 6.8%, whilst requiring only 3.9% of the labels as compared to the previous patch supervised methods. We performed two real-world deployment case studies. First, we consider the Global Wetlands dataset, which is a dataset containing images taken by a remote camera in a seagrass meadow. This emulates the scenario where an ecologist collects a new set of seagrass images. However, they may contain some objects the ecologist is not interested in or has not seen before. In this case, the fish swimming through the frame. We contribute a labeled test set of patches for this dataset and demonstrate that SeaCLIP can be effectively used for outlier detection of the fish. For the Global Wetlands multi-class case, we use CLIP to separate and generate pseudo-labels for the seagrass, fish, and background classes. SeaCLIP outperforms zero-shot CLIP by 2%, and it is important to note that it also performs inference significantly faster than zero-shot CLIP. In the binary case, our DeepSeagrass trained approach generalizes across the differences in image characteristics and outperforms both the prior approaches as well as SeaCLIP trained on Global Wetlands. In our second real-world deployment case study, we demonstrate the performance of our approach on underwater imagery collected by the FloatyBoat autonomous surface vehicle. We show that given only 20 FloatyBoat images, our model generalizes to imagery taken on a different camera with a top-down viewpoint and different scale, lighting, and visual characteristics. In this video, we can see that our model correctly detects seagrass, shown in yellow, and is also able to detect the background, shown in pink. To summarize, in this work, we presented a novel approach which only requires image level labels at training time, while still performing coarse seagrass segmentation at inference time. We outperformed prior methods by 6.8% on the DeepSeagrass dataset. We demonstrated the relevance of pre-trained large vision language models to the field of ecology and marine surveys, and showed that CLIP provides an effective signal for weekly supervised training. Further, this method could be adapted to other applications, such as mapping weeds in precision agriculture, or for coarse segmentation of remotely sensed imagery. We demonstrated the performance of our approach on two case studies, and showed that our method is computationally lightweight, fast, and able to generalize to imagery collected by an autonomous surface vehicle. We also publicly release our code on GitHub. Thank you for watching our video.